Okay, so in this video is going to be kind of our first force that we're going to break down, and we're going to look at tension. A lot of times, the reason why we're going to look at this first, because a lot of times in tension questions, you're at equilibrium, which means your acceleration is equal to 0. Okay, so remember that, or recall that equilibrium means that the object is not being accelerated. So now it can be in static equilibrium, right, which means it's not moving, or it can be in dynamic equilibrium, right, which means it's moving, but at a constant velocity. And remember, our two scientists, or our two natural motion concepts, right? The first one was Aristotle, the second was Galileo, right? Galileo, I forgot the one now. So Galileo. Okay, so Aristotle's natural motion says objects want to be at rest, which is our static equilibrium concept. And Galileo say, no, it's natural for objects to be moving with a constant velocity, which is our dynamic equilibrium. Okay, and so the force we're going to focus on here in this section, in this video, is tension. So tension is the force that is associated with ropes, cables, strings, etc. Now, you got to remember that these ropes, cables, and strings, you don't want them to stretch. So we want them to be inelastic. Okay, we don't want them to stretch to a point. So we're going to assume that if they do stretch past that point, they're broken. Okay. Now, solving tension problems will sometimes simply use adding vectors that are perpendicular to each other. Those are your easy questions. Okay. So what will be happening is that you're not going to be looking for the resultant. Right, so you're not going to be looking for what is the force that results, but what you're going to be looking for is what is called, the equilibrium. Okay, and what this is the force that creates equilibrium. Okay, so if I got a bunch of ropes tugging on an essential object, and I want to find out what force can I exert to cause all that motion to stop, I have to find the equilibrium. Okay, so now you can use the Pythagorean theorem. Right, so Pythagorean theorem, right, to find the magnitude of the force, then use the inverse tangent function, okay, to find the direction. So to find, I'll write over here, so to find the magnitude, you're going to use Pythagorean theorem, and we'll call it Ty and Tx. Okay, and then you're going to use to find the direction, you're going to use the inverse tangent function, right? And your calculator said tan to -1, and you do Ty over Tx. Okay, it's always y over x because we want the horizontal angle, not the vertical angle. Okay, so the direction of the equilibrium is found by simply adding 180 degrees to the angle found. So if I found my angle to be 22 degrees, I add 180 to it. The equilibrium is at is the opposite, okay, which then makes it at 202 degrees. Okay. All right, so let's just do a quick example here. So how much force would I need to pull with on a third string to create equilibrium if one string has a force of 20 newtons vertically and another string has a force of 50 newtons vertically, 50 newtons horizontally acting on it? So it's like I got these three strings, right, tied together, and I need to find where am I going to put that third string and how much force am I going to pull with so that I can create, equilibrium, right? So basically, here's my free body diagram, right? Again, you can do free body diagrams here, but notice that when we add vectors, we place them tip to tail. So this is my y, or my vertical, and this is my horizontal, right? Now, what really happens is to create equilibrium, I really need to find what is negative Tx. I need to find what is negative Ty, right? Because if I found what is the resulting force right now, it's going to be a piece that kind of does this. but I want that opposite piece. Right? This is what I want. Okay? And so what I'm going to do is I'm going to find the magnitude by doing Pythagorean theorem. So t equals the square root of tx squared plus ty squared. Okay? And so that's going to be the square root of 20 squared plus 50 squared, right? Because those are the two forces. Okay, so we're going to get the square root of 20 squared plus 50 squared. And that's going to give me a magnitude of 53.9 newtons. So I have to, now that's how much I have to pull with. Now we need to find the angle, right? So now we're going to do the inverse tangent of our y value, which was 20, over our x value, which is 50. Okay, so I'm going to do the inverse tangent of 20 divided by 50. And that's going to give me 21.8 degrees, right? But that would be this angle here. I want this angle over here. We can keep it at 21.8 degrees and say below negative x, right? The negative x-axis. That's also a valid way to say this. Or you can add 180 degrees, right? To give you kind of the full-fledged number, right? But typically in physics, we do want it between 0 and 90, and we just indicate like this general direction. So I would have to pull with 53.9 degrees at 201.8, oh, sorry, not 51 point, right? So I have to pull with a strength of 53.9 newtons at 201.8 degrees, right, to create equilibrium. So that is my answer, okay? Now, what will generally happen is your ropes won't be nice and pretty, okay? Nice and pretty meaning they're not going to be perpendicular to each other. They're going to have an angle between them, okay? So if this happens, right, you're going to first need to resolve, right, or decompose the tensions into components, okay? So I need to do something like Tx equals T cosine theta and Ty equals T sine theta for all of my ropes, and now I can sum the forces, okay? And so let's look at this question. So calculate the tension in the wire supporting the 70 kilogram tightrope walker shown in the figure. It's not below, it's to the right here, okay? So when I draw my free body diagram, because we're going to follow steps, draw, sum, solve. So that's the point that I'm going to look at, right? So that point of connection, okay? So I'm going to have, call this T1, call this T2, and then we have the weight of the tightrope walker, okay? So basically what happens is, what you're going to see here is that, notice that the weight is, now I'm going to draw my components on my picture, but on the AP test, you can't do this. They would take off points if you did what I'm doing right now, okay? So there are my X components, okay? And then here are my Y components. So that's T1Y, not T2Y, okay? So you can do some of your algebra here and then plug in your sine and cosine functions. So one thing I want to point out, when you have this, your two X components would cancel each other out, right? They have to be equal but opposite because there's nothing else horizontally here, right? And so if I do my T chart, right, I'm going to do T2X minus T1X equals 0, right, because we're balancing the tightrope walker. And in the Y direction, I have T1Y plus T2Y minus the walker's weight, right, and it's going to be balanced. So what really happens now, okay, so this is where I like to do this because this is where physics ends, right, and where math starts. right, is that after you sum the forces, the solve step is now just algebra, okay? And so I'm going to do T2x equals T1x, okay? Now, the angles are different. I forgot to mention that the angles are different, okay? If they're equal, then you just say like T1 equals T2, right? If the angles are the same. But the angles here are different. So it's going to be T2 cosine 3.6 equals T1 cosine 4.2, okay? And so what you're doing is you're finding a relationship that I'm going to take and plug it over into the y direction and then solve for T1 and then solve for T2 ultimately, okay? So it's like I'm saying T2 equals T1 cosine 4.2 over cosine 3.6. All right, so if I do a quick calculation, cosine 4.2 divided by cosine 3.6 tells me it's 0.999 T1. So it's very close to being, just equal to each other. And that's true because small angles, okay? And so now I'm going to solve this, right? I'm going to do T1 sine theta, or sorry, let me put in the angle. So T1 sine 4.2 plus T2 sine 3.6 minus FG equals 0, okay? And so now I know T2 in terms of T1. So T1 sine 4.2 plus T1 0.99 sine 3.6. And I'm going to add that weight over, okay? And so now I'm just going to kind of multiply all this out, figure out, okay, sine of 4.2 is 0.073 T1 plus, and then sine of 3.6 times 0.999, it's going to be 0.063 T1 equals mg, so the weight of our tightrope walker is 70 times 10, or 700. Okay, and then 0.063 plus 0.073 is 0.136 T1 equals 700. And so T1 is just going to be 700 divided by 0.136. So 5,147 newtons for T1. Okay, now I can take that over here, plug it back in over here for T2. All right, to figure out what T2 is. So 0.999 times 5147, and that's going to equal probably just slightly less than that, 5142. Okay, so there is the tension, right, in the two ropes. Now, yes, this is one rope, okay? It's one single rope, but the second you kind of break it apart by adding something to it, it now becomes two separate ropes. So this is like rope 1, and this is like rope 2. And because the angles are different, the tensions will be different. And the reason why they're very close, the angles are not that far off. They're only about half a degree off, which isn't a big deal, okay? All right, so from here on out, right, so that's tension. So I gave you one where it was equilibrium or equilibrium problem, and then I gave you one involving tension. They like to do stuff with hanging pictures. You got the tightrope walker here. You could have something similar to above there where now they're acting at an angle, okay, and you'd have to figure out what would produce the equilibrium. But you're probably not going to get a nice, smooth looking question like the first one that we went over in this video. Okay, the next video is going to deal with apparent weight, and then we're just going to keep working along with surfaces and connected objects and problems like that.